2008 Construction Innovation Forum. Nova Awards. Control of flying deck forms. The 2008 Nova Awards recognizes two innovations that offer different alternatives for this existing process. The Signal RITE compensator system innovates and improves an existing process for attaching rigging to large forming systems through a combination of technologies that reduce hazard exposure and costs while moving large form systems 30 to 40% faster. The Signal RITE compensator system is a custom-designed spreader bar, electric hoist, and remote control that are attached to any crane rigging to enhance the form-moving process on the concrete deck forms. The system is designed to work with large flying deck systems that span around 50 feet or so in length and the width of a building from column to column. The Signal RITE compensator system improves the process by attaching the electric hoist and chain fall to the compensator and controlling it remotely as forms are moved out of a building. The work crew only needs to attach to the forms once, eliminating the need to go back onto the forms to adjust rigging. The result is reduced exposure to hazards and increased productivity. The system was created by Jeff York with support from Harrington Hoist. Jeff has 25 years experience in the field and observed conventional methods for moving large forms in high-rise construction. Electric table formwork lifting. The table lifting system innovates the process of moving flying deck forms by eliminating the crane for form lifting through use of a small sectional form system. The electric table lifting system, TLS, is a pre-assembled lifting table that acts as an elevator for table forms. It has a 32-foot high vertical truss rail system that attaches directly to the previously poured concrete decks on multi-story projects. The railing has a shoe-type connection that slips over two pins that are embedded into the deck below. An electric lifting platform is attached to the rail and can lift about 2,000 pounds between floors by the press of a button via a motor on the platform that attaches to the rails. Because the forms do not need to be disassembled while moving, a crew of 1 or 2 can load the forms onto the TLS a few sections at a time, allowing for a quick cycling of forms. Because the TLS is self-powered to travel between 32 feet of floors, the need for a crane to move forming systems between floors on multi-story construction projects is eliminated, and crews are exposed to fewer fall hazards. Furthermore, cycling times are improved compared to conventional systems, as crews may be reduced by up to 50%. Finally, the TLS can operate in higher wind speeds than cranes, thus improving project schedule, and can be applied to any multi-story project that has cast-in-place concrete decks. The Doka Corporation is responsible for this innovation. Square Cut Plunge Saw. The Square Cut Brick and Mortar Plunge Saw uses a unique orbital cutting motion with two forward-facing blades that combine to perform both a hammering and cutting action. This patented cutting action is distinct from conventional cutting technologies like disc cutters and cuts deep and square without overcutting in the corners, providing precision, accuracy, and control. It is also safer and produces significantly less dust than conventional cutting tools. The brick and mortar saw uses two side-by-side blades which move in a small elliptical orbit at a frequency of approximately 5,200 orbits per minute. The blades are driven 180 degrees out of phase for balance and efficiency. Because the blades only cut on one edge and do not rotate like a circular blade, they do not require guarding, and can assume a variety of shapes to suit various applications. The cutting action is created as carbide teeth hammer into the material, while a high-torque stepping motion excavates the waste towards the rear. The cutting action does not depend on sharpness because each carbide tooth behaves like a small hammer to achieve the cutting action. Due to the high-frequency hammering action, high torque, and low surface speed, the saw does not grab or kick back, and it is possible to plunge the blades into the surface of a wall at any point. In addition, because the blades are not circular, it is possible to cut square to the full depth of the blades. Inventor Kevin Inkster, co-director of Arbotech Industries Limited, developed the technology from his experiences as a woodworker in a forestry town in Western Australia. In 1988, Inkster and his wife Kristen Inkster founded the company Arbotech to commercialize a range of cutting tools he had developed, including the brick and mortar saw. Offshore deck salvaging system. VERSABAR bottom feeder. The offshore deck salvaging system, or bottom feeder, was specifically developed for the lifting of structures as single units from the seabed in depths of up to 400 feet beyond, with a maximum safe lifting capacity of 4,000 short tons. The bottom feeder was developed specifically for the purpose of addressing a need to retrieve nearly 130 rigs that were lost in the Gulf of Mexico during the destructive 2004-2005 hurricane seasons in water depths beyond the operational limit of divers. The bottom feeder is made of 2 barges, each 255 feet in length, joined by a 130-foot truss with winches and cables. The barges are hydraulically decoupled and are capable of moving independently of each other. Lifting is completed via the application of 4 independent pairs of lift blocks with a rated capacity of 1,000 tons each and suspended from a twin truss system. The use of independent lift blocks with 45 feet by 80 feet spacing provides significant flexibility to efficiently distribute lift loads into the structure and accommodate structures that are significantly out of level at the time of lift, as well as unknown lift weight and center of gravity location. In conventional derrick barge operations, the block that transfers the load back to the barge is positioned outboard of the derrick and barge unit, losing efficiency and requiring near ideal conditions to operate. One of the main advantages of this innovative lift system is that loads are transferred to the truss frames and then to the barges through the blocks vertically positioned over the lift. The 3D space frame nature of the structure also provides significant out-of-plane or slide load capacity, allowing for structures that initially lift out of level to be lifted and re-leveled without the need to re-rig. In addition, a patented decoupled joint or pin-in-pin system on each of the trusses on opposing sides of the barge allow the system to operate without transferring the hydraulic loading from C-action to the trusses. The bottom feeder reduces the mass of the system of barges and lifting equipment needed for whole platform salvage because of the centricity of the loading during the lift. This translates into significant cost savings over the conventional methods of salvage. Secondly, the independently functioning joints allow the system to operate within much more severe weather conditions than conventional systems. This is because the loads generated by wave action are not transferred directly to the bottom feeder trusses, but are absorbed by the barges and the unique sleeved joints. John Khachaturian, president of VERSABAR, was the person primarily responsible for the innovation. Golden Gate Seismic Retrofit Project, Phase 2. The Golden Gate Bridge Seismic Retrofit was initiated to address the impact of an earthquake of sufficient magnitude to cause major damage or even to destroy this historic landmark. The second phase of this monumental project features a number of innovations that were developed during planning, design, and construction, including the following 4. The pin-bearing uplift system. The four-point arc is a steel arch truss structure approximately 320 feet long and 185 feet tall, seated at each end on 4 steel pin bearings. The steel four-point arch structure was modified into a huge energy-damping element, allowing the structure to uplift up to 1 inch vertically from the bearing pins and then return to its original position when the arch is subjected to seismic ground motions. This was the first such design to provide a practical method of retrofitting existing steel pin bearings to enable partial ground isolation. Energy dissipation devices dissipate energy by means of abrasive friction force. The device is comprised of a bronze disc sandwiched between 2 steel plates fastened to a system of steel beams, which are connected to the existing structures, and of clamping steel rod assemblies. By adjusting the clamping force, the device initiation force and friction force can be adapted to obtain the required damping characteristic. The pylons. The centerpiece of the Phase 2 retrofit was the strengthening of the 2 massive 220-foot-tall hollow concrete south pylons. The pylons were amended so they could dampen seismic energy through rocking motion and resist uplifting at the bases, overturning, and lateral sliding. The south pylon retrofit comprises of partially stressed and partially unbonded large-capacity tie-down anchors, each with a 2 million-pound capacity installed at the perimeter of built-up and heavily reinforced pylon foundations. This provides partial fixity that prevents overturning but allows controlled rocking under the ground motions. Steel plating installed full height on the exterior and interior pylon wall faces to provide wall tensile and compressive capacity necessary to withstand demands of a maximum credible earthquake. A 4-inch thick layer of reinforced cover concrete cast over the exposed surfaces of the exterior steel plating to replicate the original historic architectural concrete appearance of the pylons. Cheese plate design. One of the design criteria of the seismic retrofit was that all work must be performed while the bridge was open and under continuous traffic, connecting the new steel plates to the existing steel plates and replacing rivets with much higher capacity high-strength bolts while maintaining the integrity and load-carrying capacity of the connection posed a huge constructionability problem. The solution utilized a steel plate with shop-drilled holes, matching the existing fastener pattern of the connection. The diameter of the holes was slightly greater than the diameter of the existing rivet heads, and the thickness of the plate matched the height of the rivet heads. The resulting plate resembled a piece of Swiss cheese and was named a cheese plate. The cheese plate method enabled the new strengthening steel plate to be installed and clamped onto an existing gusset plate with the cheese plate in between. Then, using the new plate as a template, the existing fasteners were drilled out and a new fully tensioned high-strength bolt installed in their place, one at a time. The persons primarily involved in the innovations are Thomas C.G., P.E., and Marvin Young of Thomas G. and Associates, Quang Lim, P.E., Ph.D. Congratulations to the 2008 Construction Innovative Forum NOVA Award recipients.